So going back to here, this tells us at 50 degrees Celsius, you cannot dissolve more than 42 grams in 100 grams of water. If you put more than that, it's not going to dissolve in the water. It's going to fall out to the bottom. Can you think of any way that you could force it to dissolve? I think I already said it last time. Y'all remember? So again, so if you put 43, let's say you put 43 grams in at 50 degrees Celsius. 42 grams will dissolve, and 1 gram would sink to the bottom. You cannot get that 1 gram to dissolve at 50 degrees Celsius. So how could you, at 50 degrees Celsius, get that 1 gram to dissolve? And that won't work. When can it actually hold 43 grams? A higher temperature. But if you cool it off, so if you bump up its temperature, to 60 degrees, it can now hold, so coming over here to 60 degrees, it can now hold an additional 3 grams. It can now hold 45. Now, if you reduce the temperature back to 50, that 3 additional grams that's dissolved in just won't immediately appear and fall down. For a very brief period, it will be something called supersaturated. Now, if you shake it, eventually that 3 grams will come out and fall down to the bottom. There are certain chemicals that are more stable than others, but for the most part, to get super saturated, what you have to do is increase the temperature, what allows you to dissolve more things, and then you reduce the temperature back down, and if you do it very carefully, you can keep that additional 3 grams, for example, dissolved into it. It's not permanent. In most cases, that 3 grams will eventually come out. But that's how you can achieve supersaturated substance. So let's look at sodium chloride. So sodium chloride, what temperature is this? It doesn't say. So for unsaturated substance, you put 30 grams in, and you get it all dissolving. You could probably put in more grams into the water, and it'll dissolve more. So if we go back to this graph, sodium, you can put over 30 grams of sodium chloride, the blue line. So this sodium chloride table salt. For temperatures between 0 and 100, you can put in about 35 grams or so, 35 to 40 grams. So in the case of this, it doesn't say temperature. But putting 30 grams into 100 grams of water, obviously the 30 grams is going to dissolve. This would be unsaturated. A saturated solution is, let's say that we put 40 grams in. 36 grams will dissolve, and we have 4 grams to sink down to the bottom. That remains undissolved. This would be saturated, meaning that any more over 36 grams you add is just going to sink down to the bottom. So even though you put 40 grams into it, and we're over that 36 gram threshold, it's still considered saturated. Does that make sense? Because that's the difference between saturated and supersaturated. Supersaturated would be if we force that 4 grams to dissolve. Here, So, an unsaturated solution is when you add less than the maximum amount of solute. That can dissolve to a solution. A saturated solution is when the maximum solute is dissolved in solution. And supersaturated solution is a special case when more than the maximum is dissolved. And that's the key word, is dissolved. So let's look at this scenario. Let's say that we have some chemical. Suppose the most of some solute that can dissolve in 100 grams of water is 50 grams. Suppose, so we have some chemical, it's, in other words, its solubility is 50 grams solute per 100 grams of water. So the most that can dissolve in water is 50 grams and 100 grams of water. So if we put, for example, 25 grams solute, this would be unsaturated. If I put 49 grams of solute into the water, it's not at 50. This would still be unsaturated. We can still make 1 gram of solute dissolve. So these two, bless you. So if we put 49 grams of solute into the 100 grams of water, in each of the examples we have 100 grams of water, this would still be unsaturated because we can still put in 1 more gram. Now if we put 50 grams in, This would be called saturated. All the solute has dissolved. And no more can be dissolved. If we put in 60 grams of solute into this container, 50 grams will be dissolved, and 10 grams will precipitate to the bottom. This is still saturated. It is not supersaturated. We did not get more than 50 to dissolve. And we can no longer, and we cannot add, and we cannot get any more to dissolve. So this case is still considered saturated. So we're putting more than 50 grams in, but this would still be considered saturated because that 10 grams didn't dissolve in it. It wouldn't be considered supersaturated unless we force those 10 grams to dissolve. Does that make sense? Supersaturated. Everyone go with the notes. So supersaturated solution is, so this picture is showing the addition of 100 grams of glucose to 100 milliliters of water at 25 degrees Celsius. Note, at 25 degrees Celsius, only 91 grams of glucose will dissolve in water. So what ends up, so only 91 grams can dissolve if we put 100 grams into it. So that means that, so as we keep adding, only 91 grams will dissolve into it. So only 91 grams will dissolve, 9 grams won't. Now, if we increase the temperature from 25 degrees to 50 degrees Celsius, we can force that 9 grams to dissolve. And it will become unsaturated. We can still add more of this. We can still force more sugar to dissolve into this. Now, if we cool it down slowly from 50 degrees Celsius to 25 degrees Celsius, that additional 9 grams won't immediately come out of solution. It won't just magically fall out. And we call this, so precipitate is the substance that falls down to the bottom. We can make it super saturated. An example of this that we use is syrup. Syrup is a super saturated form of sugar and water solution. So what this means is if you sprinkle any sugar onto some syrup, There's no possible way you can get the sugar to dissolve into it. It's super saturated, so it can't dissolve any more sugar. But at the same time, because it's super saturated, the sugar doesn't immediately fall out of solution. Sugar happens to be more stable than a lot of chemicals. Salt water, for example, is more unstable. If you were to try to make a super saturated form of salt water, so get more salt to dissolve than usual, it would be very unstable, and as soon as you cooled it off, the salt will come out of solution and precipitate down to the bottom. So the key to getting something super saturated is this step right here, the cooling it slowly. If you were to rapidly cool down, so if you were to put some sugar into, have anyone ever made candy? Rock candy? So what you do, you basically added sugar and water. And how'd you cool it off? You just let it out in room temperature, right? And then initially it was like a syrup. And then as you let it go from being hot to room temperature and air, it kind of cooled off a little bit quickly. It didn't stay super hot. You didn't control the temperature at which it cooled off. And then all of a sudden it turned super hard. If you were to sat there with the temperature and just slowly adjusted the temperature, let it cool off very, very slowly, you could have left it at that goo stage. You could have made it into a syrup. And it would have stayed into a syrup. So the trick to keeping it a super saturated solution is to cool it off very slowly. What this does, the reason why that works, is if you can imagine so we have random water molecules all around. And when we put in, I'll use squares to represent sugar. We have water molecules all around. If something is not saturated, then these water molecules are going to be constantly banging up against the glucose molecules. They'll keep them in solution. They'll keep them bouncing around everywhere. Eventually, if you keep adding a lot of sugar molecules, there's not enough water molecules to keep hitting this sugar to prevent it from falling down due to gravity. So eventually what would happen is these sugar molecules are not being hit enough by the water molecules, and they'll eventually sink down to the bottom. And if we increase the temperature, we're increasing the speed at which these molecules are moving. So we're giving them more energy. So we increase the temperature, they have more kinetic energy, and can bang these particles up more. If you cool it off very, very slowly, however, you can force these glucose molecules to kind of be locked into place. You'll be squeezing water molecules in between it, and as it cools off slowly, it'll become more thicker and thicker, and these sugar molecules have no place to fall out of solution because you allowed the water molecules to squeeze in between the glucose and that. They're usually typically very unstable. Glucose likes forming long chains, and what happens is the reason why glucose is more stable than others is you end up with these long chains of glucose, and the water molecules are able to squeeze and separate out and keep pushing up these chains. And these chains are not straight, they're curl around. And we have water molecules just pushing them. And all these water molecules keep it suspended and distributed. And as long as you don't do it quick enough, that if you do it slow enough so that the water molecules can keep in between these chains, they can keep it suspended in the solution. Let's see if I can find a video of super saturated. So he put in some sugar, he's now adding some water. Go boil it until all that sugar is dissolved. So as he continues heating up, he's increasing how much sugar can dissolve into the water. And this is this would technically be saturated sugar. Sugar water, this is a solution. And he's going to force it to come out by adding a place the crystals can grow onto. So over time, these crystals can come out of solution because this is super saturated at the lower temperature, and you can actually grow sugar crystals off of it. This is actually how they make rock candy like this. You can see that the sugar is dissolved in the water, but it's super saturated, so it's going to want to come out. Another thing that determines whether or not how stable it is sugar has to form crystals. So in order for it to come out of solution, it has to form a giant crystal. And if your beaker is very smooth, it won't grow crystals on the side of it. And if you just have pure sugar and pure water, then there's no place. If you add like flavoring, like peanut butter to it, if you ever had peanut butter candy, which is just sugar, peanut butter, and water or milk, then the sugar crystals can lock onto the peanut butter, and the whole candy hardens really quickly. So if you add like peanut butter or something to it, then it's going to harden because the crystal can grow off the peanut butter molecules. If you just have pure sugar and pure water, there's nowhere for the crystals to start growing on. This is the reason why he's adding something. So the crystals are going to very slowly start going off of the string and this washer. So now that you've added some place for the crystals to grow, they can come out of solution. Also, the bottom of the glass is probably scratched up. Hence the reason why you see crystals growing down here. Have I showed y'all super cooled water? Yeah. So again, in order for a crystal to form, it has to have a nucleus or some site for it to grow. So if you have super cooled water, so if you were to put water in a freezer, like this, this water is probably at -10, -15 degrees Celsius, below the freezing point. So it's super cold water. It's below its freezing point. It should be frozen, but there's nowhere for a crystal to start growing. So he hits it, and it made a crystal grow, and now the water is slowly building off that one crystal. So he has some ice down here, so he already has some crystals. So when he pours water onto the crystals, they start forming on the surface of that previous crystal. And so you're constantly growing crystal after crystal after crystal. Since the water is already below its freezing point, it wants to turn into ice or a giant crystal. But unless it has a starting point, there's no place for it to go. That's also how you can get super critical ones. So things that have a regular pattern. Salt crystals, because it's just NaCl. Its crystals don't have to be that balanced. That's the reason why it's super hard to get supercritical solution of salt, because for its crystal to grow, you don't need a unique pattern, because it's only two atoms. They can just link up really easy. So glucose molecule. So a glucose molecule looks like this. So it's very difficult to grow a crystal from this structure. Here's another look at it. This is the other one looks like two parts. There's a glucose. So it's very hard to grow a crystal off of this. So you kind of need a starting place, because when you try to get two glucose molecules to bond to each other, they kind of bond at weird angles, and you can't grow a crystal off of it. So you kind of need a starting place where the next glucose comes in, and it can only bond in one way. Water, the same thing, has a unique pattern. Because it's polar, it has this weird shape to it. And so in order for another water molecule to come and build a crystal off of it, you're going to have to get a unique pattern. Let's see. You have to get these chains of them like this in order for it to actually become ice. Technically, though, ice crystals are shaped like this. This actually is the reason why snowflakes grow like this. You ever seen a picture of a snowflake? You see them at this hexagon shape. Because when it turns into ice, the water crystal has to arrange itself like this. Really advanced chemistry going on in it. But unless you already have this starting location right here, just bonding like this doesn't really produce, these particles can fly past each other, which means it's still liquid. In order for the particles to be locked in place, it has to form a crystal like this, so that the crystal structure can grow on it like that. Trying to see if I have another PowerPoint. Yeah, yeah. So a little review. I don't think this has any additional things. So a solution is a homogeneous mixture of two or more substances in a single phase. One constituent is usually regarded as a solvent, and the other a solute. So solute is the part of a solution that is being dissolved, usually the lesser amount. Solvent is the part of the solution that is dissolves, usually the greater amount, and when the solute and solvent combine, it creates a solution. So hot chocolate, we have milk being the solvent, and solute would be cocoa powder. Soluble, I think I already went over this. Substance that can be dissolved, a substance that cannot be dissolved is soluble. Miscible refers to liquids, a liquid substance that is soluble in another liquid. Immiscible is a liquid substance that is insoluble. So here we can see miscible is the one on the left, we can see two clear liquids. Solid solutions are known as alloys. I wanted to get so nonpolar electrons are shared equally. Fats and oils are considered nonpolar. In polar molecules, the electrons are not shared equally. So, like with water, the oxygen absorbs more, or pulls more strongly on electrons and become negative, while the hydrogen is positive. That's the difference between nonpolar and polar. Nonpolar is all the electrons are shared equally, and in polar, the electrons are not shared. Again, I said the main thing to remember is nonpolar dissolves nonpolar, and polar dissolves polar molecules. Like dissolves like. So water molecules are more polar because O is. We'll go more into electronegativity later in the year. Again, a lot of times in science, we go into things before we actually learn more in detail. Like solubility, the reason why things are polar we'll learn later. It's just this expression that you really need to know. We'll talk in later in the year how to identify something as polar or nonpolar. Water is polar, oil is nonpolar. Which of these will dissolve the fastest? We all have the same amount. See, why? Because there's more surface area. So stirring, temperature, and surface area are crushing it are the ways to increase. What does aqueous solution mean? Aqueous means the solvent is water. And it's not that soluble in water, it just means that your solvent is water. If the solution can conduct electricity, it's known as an electrolyte. Did y'all know that water can't conduct electricity? Pure water. It's actually one of the best insulators. It's one of the best things to protect your stuff from conducting electricity. The problem is, if you get the tiniest amount of ions into it, it becomes an electrolyte. So if you sprinkle a little bit of salt into it, it can now conduct electricity. Let me show y'all a picture of this. Any of y'all ever heard of the Z machine? This is like one of my favorite pictures of all time. I really want to hide. Alright. So, this is the Z machine. It produces the highest concentration of electricity to a single point. It is so powerful that you cannot prevent electricity from arcing everywhere. In order to reduce it, they use water. Because water is literally one of the best materials. They fill us up with water, and even despite that, we can still see arcing in the air and around it. It produces the most powerful X-rays in the world, or actually almost in the universe. It's what they use to study black holes by producing X-rays on the same level as black holes do. Imagine taking several cities worth of electricity and pumping all of that electricity down to the size of a penny in 1 nanosecond. In order to protect everything, they fill the entire room with pure water. And as I said, you have to have it pure. If there's any salt on the floor, if you bring in dirt on your shoes, when they're in that room, they're all inclusive. It's not that bad. Pure water, again, that's a lot of water. And then you test the ions in it to see if it's safe. But you can already see it doesn't help that much. That's just arcs of electricity. Again, it's pure, clear water. And there's the target area where all of the electricity goes. Here's the room itself. I guess technically this person's not in it. I guess down here is where it's most. See people in clean going into it. All the art front. That's the room. They fill these things with pure water to prevent them. I wanted to go over and do some more examples. So if you have salt water, you can cook up electricity. Very conductive. Sugar doesn't produce ions, so it's not an electrolyte. So I wanted to go in. So rate of solution is increased temperature, pressure, and stir. Well, so your electrolytes is just another fancy way of saying salt. You need salt. Yeah. So have y'all had anatomy and physiology or biology? I don't know if they go over in biology enough how your cells work. If you have sodium and potassium controlling ion levels, and that's how your neurons fire. Is you have sodium pump and potassium pump that will send charges out, or it'll pump sodium into a cell, making it more positive, and that means the outside of the cell is more negative. And as that charge difference builds up, you can have a static electricity shock between the end of a neuron and another neuron. And that's how electricity flows in your body. And so, especially with muscles, so anytime you want to squeeze, cause the muscles to contract, you send electrical signal down to your muscle, which causes them to contract. So if you need electrolytes, you need that sodium ion and then your potassium ion to do the reactions. Otherwise, you can start getting cramps and stuff if you exhaust the sodium and potassium. So, types of solution. So, unsaturated is the solution in which more solute can dissolve. It's below the line. Saturated is a solute in which the contains the maximum amount of solvent. It'd be on the line. You can also have some of it dissolved out. And a solution in which contains more maximum amount of solution, and it'd be above the line. The solution is holding more solute than it should be able to. This is achieved by heating the solution and then cooling it very slowly. Rock candy is also considered an example of supersaturated solution. I guess it doesn't have to be liquid, but that is supersaturated. Supersaturated are unstable. Supersaturation is usually considered temporary, as there's going to be a change where it falls out of solution. If you cool it off slow enough, though, when it comes out of solution, you still have water and solute trapped in there. Whenever it turns into a crystal, you're also trapping water molecules in it too, sometimes. I like this chemical, I forget the name of it. It's used in Kotex. So solubility, how much time do we have? So solubility indicates the amount of solute that will dissolve in a given amount of solvent at a specific temperature. Or x-axis is temperature, or y-axis is how much solute will dissolve in a higher gallons of water. And then we have various lines. So if it's on this line, it means it's saturated. And this is talking about how much is dissolved, not how much you put in. So back in that example I drew, if you put 60 grams of that chemical into the water, 50 grams will dissolve. This is talking about how much has dissolved, so only 50 grams, so you would be on the line and 10 grams precipitating out. If you're above that line, if you have more than that dissolved, it's supersaturated. If you have below that amount dissolved, it's unsaturated. If you're on the line, it's saturated. This is what I want to go into. So, classify the following as unsaturated, saturated, or supersaturated. And this would be referring to that amount dissolved. So, 80 grams of sodium nitrate at 30 degrees. Is that unsaturated? Yes, it's below it. So unsaturated. 45 grams of potassium chloride. So we're right on the line. So we're saturated. Potassium chloride. So the last one would be